Welcome to Academic Daddy's class. Today we're going to be treating system. We say that a system, chapter 4, that a system is a region or space hmm, uh, in a surrounding. Some textbook will say excluded from a surrounding, but surrounding is the bigger space. Where reaction can be chemical reaction occurs. Reaction occur. Let's use occur. So what I mean is this: if this happens to be the environment, and I choose to make room for a basin, let's say this is a bowel, and inside this bowel, or let's say this is a conical flask, inside this flask I decide to perform certain experiments inside this. Everything about this containing vessel is a system. Just like your classroom. If that classroom you enter and you are learning, as you are learning, the surrounding is what we consider universe in thermodynamics. I've done video on that. Why that part where a situation is taking place or something is taking place is what we call system. And in this system we have two major types. We have the open system. So open system is a region or space where reaction occur and with provision for external influence like temperature, heat, air, all those kind of things, pressure. But any system whereby external influence, external forces are being prevented from entering is called a closed system. So a space or region where reaction occur under influence or external influence is known as open system, while a space or region where reaction occur without the interference or without external influence or external forces is what we call closed system. But this is not what we are doing today. I just had to introduce it so you get to know it. But what we are looking at is what we call properties of a system. And these properties of a system, the one we are going to be looking at is what we call colligative property. Colligative property or properties. So we say that properties of a system, these colligative properties of a system, is a physical property. It's a physical property. Or you say it's the physical property of a system. It's physical property of a system when the number of moles is increased. So it's the physical property of a system when the number of moles is increased. Or we can say that it is the physical property of a system that is concerned with the number of moles of solutes added to a solvent. We can also say that colligative properties of a system is the physical property of a system concerned with concentration of solutes in a solvent, of ideal solution. So whatever we are doing today under this colligative property, you have to know that it is simply talking about if I have solvents, it is comparing what the solvent is and what it becomes when you add solutes to it. That is what colligative property is talking about. The things that happen to solvents when you introduce concentration to it. And remember, we have limitations to what we are going to be treating today. So first of all, let's consider the limitations. The first is that whatever solute you are adding, even if it dissolves, as it dissolves, we are considering it in such that it dissolves, but there should be no association or dissociation of particles. When I mean association or dissociation of particles, it means no forming of ions. No forming of ions. If we are getting these facts straight, that means we can be able to use colligative property to find relative molecular mass. So whatever we do with colligative property helps us in finding relative molecular mass. And for that to happen, there should be no dissociation or association of particles, which means that if there's no dissociation or association of particles that we'll be dealing with under this topic, it's not like we can't have other particles that have ions and the rest. But when we want to look for relative molecular mass, particles we deal with are particles that are of organic compounds. Things like sucrose, glucose, urea, etc. So those particles that you very well know that when it dissolves inside solvent, inside water, I told you solvent is the large molecule, the one that is doing the dissolving, while solute is the one that gets dissolved. So those particles that when they enter water, they dissolve, but they don't dissociate into ions. That's what we deal with when we are treating colligative property in order to find relative molecular mass, because the idea of everything we are going to be doing here is simply to use it to find relative molecular mass. That's the basic idea. So number 2 is that there should be no chemical reaction. So whatever we are dissolving, the solute we are dissolving, does not react with the solvent. There is no chemical reaction, it just dissolves. That's what we are treating. Number 3, it should be in such a way that it is a diluted solution at the end of the day. By the time we add the solutes, even as we add the solutes, we are making sure that the solvent is more. And I know you know that anything diluted or dilution means having less particles, while concentrated means having more particles. So it should be in such a way that even as you add particles, the solvent is still very far enough larger or more than the solutes. So number 4, the fourth limitation of what we are treating today is you have it now. All right, the fourth limitation, which is also the same thing with this diluted solution. So if it's diluted, it needs to be in such a way that the idea you have when you're treating colligative properties is that whatever you're adding should be of non-volatile solutes. Non-volatile means it does not evaporate readily, it does not evaporate easily. So it should be such that non-volatile solutes is added into volatile solvent. So the solvent has to be the one considered volatile, such that it is the one doing the evaporation into volatile solvent. Remember that the key idea of what we are treating is still revolving around our ideal solution. So once I know these limitations, we can now treat the types of colligative property. There are 4 basic types of colligative properties. So let's summarize it quickly so that we can solve problems on this. So the 4 basic types colligative properties. So we have number 1, relative lowering of vapor pressure. Vapor pressure is not a colligative property, but the relative lowering of vapor pressure, that is change in vapor pressure. Then number 2 is what we call elevation of boiling point. Number 3 is freezing point depression. Number 4, osmotic pressure. Represent this with pi, represent this with Tf, represent this with Tb, then represent this with change in P. Alright, so let's start with the first one, relative lowering of vapor pressure. So number 1, relative lowering of vapor pressure. So we cannot start this without talking about a man called Van Bobo. Van Babbel. Now this man said that if I have pure solvents, that what it has is pure vapor pressure, and then I come and add a solute to it, that this solute will come with its own vapor pressure, which is vapor pressure due to the solution, and that it is directly proportional to the pure, that is the pure vapor pressure. So that's what it means is that lowering of vapor pressure is directly proportional to pure vapor pressure, which means that anything occurring or anything happening to this is such that the pure vapor pressure will always be higher, So if there's any introduction of solute, that it is going to cause the pure vapor pressure of the solvent to drop once you introduce solute. So he now said that if that is case, introducing a proportionality constant, that this now becomes equals to Kp naught. So when he did this, we know that there is a man called Raoult, and that he gave us the law. He gave us the law that that vapor pressure is equals to pure vapor pressure multiplied by mole fraction, and mole fraction of the solute. So he also said that X mole fraction of solvent plus mole fraction of solute must always equal to 1. So he now said that if that is the case, let's make this now. X2 mole fraction of solute is equals to 1 minus X1. He now said that if that is the case, that this K is actually mole fraction of solute. Then you have your P naught equals to P naught minus P. That is, and P is vapor pressure, partial vapor pressure, or vapor pressure due to solution. That is solute in solvent. Why this one is just for the pure solvent. So he did this, and when he did this, he said that if you happen to replace this X2 with 1 minus X1, you will have 1 minus X1 all into P naught minus P. And if you do the maths, you have this to become P naught into minus P naught X1. We are doing mathematics now. P naught minus P. And notice that if that be the case, if this is P naught minus P naught X1, you can very well see that something can happen here. I can try to make this subject of the formula. Shebi? Yes. I can choose to make it subject of the formula. And when I make it subject of the formula, let's check if or wait, see, as I'm having this way, this way. Let's say I still have this. Let's try to make P naught subject of the formula here. So if I have P naught, this P naught, everything here, now I'm rewriting it. I've not started doing the math. X1, then P naught. So try to make subject of the formula is the sentence that says divide both sides by 1 minus X1. P naught minus P. So we can do this. We can actually do this. But this is not the knowledge, the idea he used. Minus X1. So this will cancel this so that I have P naught is equals to P naught minus P all over 1 minus X1. Should Yes. Yes. Okay. I think if you check it out, let's just be sure. So I said I said Van Babu give us P naught minus P, direct proportional to P naught. And he said that at proportionality constant, we have P naught equals to K P naught. But Routs quoted this is equation and now said that this x K is actually mole fraction of solutes. So multiplied by P naught equals to P naught minus P. So he tried to use this to prove the idea of his equation. So we made mistake earlier. So this is going to be making the subject of the formula, mole fraction subject of the formula. You now have divide both sides by P naught. P naught. So that this will cancel this. So whichever way, assuming we even use this, it will still work. But it's just that we want to use Van Babu. That is this Van Babu's law, lowering of vapor pressure, to prove Routs' law. So that means that this is what Van Babu gave us. So making this subject of formula, we now have that this is the sentence as saying P naught over P naught minus P over P naught. The LCM is still P naught equals to, and x2, he gave it to be 1 minus x1. So equals to 1 minus x1. So we now have this will cancel this to get us 1 minus P over P naught equals to 1 minus x1. Now notice that at this point we can collect like terms. We can say minus P over P naught is equals to minus 1 plus 1. That is this crossing over because minus 1 plus 1 minus x1. This becomes 0. So we now have minus P over P naught is equals to minus x1. So anything standing on this one is over 1. Minus minus will cancel. So that I now have P over P naught is equals to x1. Now, cross multiply, you get, if you cross multiply, you get P is equals to P naught times x1. So, and this is Routs' law. So he used this to prove that's his principle. So when you have this, what it simply means now is that if I get a question that asks me to find relative lowering of vapor pressure, I need to know that by what is done here, that once I add solutes, lowering of vapor pressure is reduced. So it's more like if I come here now, of all these four, when I add solutes, vapor pressure is reduced. When I add solutes, elevation of boiling point is increased. That is, boiling point is increased. Then when I add solutes, freezing point is reduced. And when I add solutes, osmotic pressure is increased. So you see, vapor pressure and freezing points will go down, while boiling point and osmotic pressure will go up. You need to know these two things once solute is added. So now, if I'm given a question to find the relative lowering of vapor pressure, I simply use the formula, which is this formula, this point, this place where I have P naught minus P all over P naught equals to x2. That's just what I use to solve anything relative molecular mass from vapor pressure. So how do I mean? See what I mean. So if I have P naught minus P equals to K P naught, this is Van Babu's law. Then Routs now give us P naught minus P equals to x2 P naught. And when you divide both sides by P naught, you have P naught. Now, you need to know that x2 means mole fraction of solutes. And mole fraction of solutes is such that is your Fn2, that is mole of solutes, all over mole of solvent plus mole of solute. But since this is diluted solution, since it's a diluted solution, it means that the solvent will be too bigger than the solutes. So we ignore the N2 whenever you are adding it, because if you add the solute and the solvent, the solute is going to be small. Since it's diluted solution, we look at when we are treating this colligative property in order to find the molecular mass. So this is going to give us N2 is equals to X2 is equals to N2 over N1. This is more. So we now need to remember that mole is the same thing as saying mass over molar mass, and this is mole of mass of solutes, then molar mass of solutes, and then this one is mass of solutes all over molar mass of solvent. Sorry, this is mass of solvent all over molar mass of solvent. I'm using 1 for anything solvent, then 2 for anything solute. And you need to know that why I'm using W here is that in chemistry, mass is considered to be weight, but in physics, mass is considered to be apparent weight. So I'm using the W to differentiate mass from molar mass, and so that I can be able to differentiate molarity too, because if I use small m and capital M, I'm now confusing it with molarity and molarity. So W stands for the mass, M here stands for the molar mass. So see, I have W2 over M2 divided by W1 over M1. Applying indices, this becomes W2 over M2 times M1 over W1. This is the same thing as saying W2 M1 all over M2 W1. So this is what I'm going to make use of. So anywhere I see X2, I use this to replace it. So X2 means mole fraction of solutes. Remember that the whole idea of colligative properties is about what happens to solvents when you add solutes. So solutes is what is causing everything that is happening. So I'll replace this now. So I'll now have, instead of X2, I'll now have W2 M1 all over M2 W1 is equals to P naught minus P all over P naught. So this is what we use. And you need to know that everything here is also the same thing as saying change in pressure is equals to W2 M1 all over M2 W1. Let's say they did not give you pure vapor pressure. They did not give you pressure due to solution, and they gave you the change in pressure. They give you a figure. Just use this to solve it. So, and you need to know that in any question given to you, M1, molecular mass of solvent, is always constant because it will be given. They can tell you it's water. If it's water that is your solvent, this is 1 times 2 plus 16, which is 18 gram per mole. That is your molar mass. It's always constant. If also you are given molar mass of, let's say they give you glucose, or let's say, let's look for a question here. Let's say they gave me, yes, let's say they gave me, for example, sucrose. They gave me sucrose. They say C12H22O11. The molar mass is simply going to be 12 into 12 plus 1 into 22 plus 16 into 11, which is going to give me around 342 gram per mole. So the molar masses are always constant, except in the case where they tell you to calculate the molar mass of this. Maybe with what is given that you should calculate the molar mass of this. That's when you know that this is not constant. Or when they tell you a solute X or a solute Y, then you know that this is not constant. But in any case where you are given the molar mass and that is not what you are asked to find, these two are always constant. So in some textbook you will see to find relative vapor pressure to be P naught minus P1 all over P naught equals to W2 all over M2 W1. And when you now want to find the relative molecular mass, it's always of the solute. If you make subject of the formula, you will now have M2 is equals to W2 P naught all over P naught minus P1 multiplied by W1. Hope you understand it, because I did cross multiply. And when you do cross multiply, you should have, first of all, P naught minus P1 times M2 W1 is equals to P naught W2 So divide both sides by the coefficient of M2, so that you now get both this one and this one multiplying, then dividing. So this is the formula you make use of to find the relative molecular mass of solutes when you are asked to use vapor pressure. Once we start solving question, you will get to understand better. So let's treat lowering of boiling points. Lowering of boiling points. Elevation of boiling points and lowering of boiling points. So number 2 is elevation of boiling point. So let's say I have a graph for this, and I know that boiling point talks about temperature. We say that boiling point is the temperature at which the saturated vapor pressure is equal to the atmospheric pressure. What it means is that when you put a liquid inside a container, that while it's not evaporating immediately, it's because there are external pressures acting around it, keeping it down. But the minute you heat it, apply temperature. That temperature where the vapors above the liquid can no longer be held back by the atmospheric pressure, and it starts boiling, starts leaving. That is what we call the boiling point. And this normally happens at 100 degrees C at 760 atm or 760 millimeter mercury, or you say 1 atm, 760 millimeter mercury. So once you know this, we can apply it. So we can say that elevation of boiling points now is simply going to be the difference. We can say it's the difference between the boiling points of difference between the boiling point of solution and that of the pure solvent. So the difference between the boiling point of the solution and that of the pure solvent is what we call boiling point elevation. So notice that if, for example, I have this to be P0, the minute, let's say this is P0 and this is pure solvent. Let's say this is solvent. As I heat this to a particular temperature, 100 degrees C, it will start boiling. And notice that at this point, if I come and add a solute, I've formed a solution. And when I add these solutes, notice sometimes if you are boiling water and it's heating, you go and put indomie or put rice, it will stop boiling for a time. It will stop for a point, then before it start boiling. That means you've made it wait or take longer to start boiling. So you've increased the temperature normally for it to boil. So that increase is what we call elevation of boiling point. So if I add solutes now, it will make the temperature, normally it's supposed to boil at this, but it will make the temperature to take longer time or take more time in order to boil. So for before it can attain that point, you say that you've elevated the boiling point. So it can now happen maybe at 120 degrees C. Yes. So the same thing, if let's say I add another solution, another solute. This is solution 1. If I add another solute, I formed solution 2. It will boil at, let's say, 130 degrees C. It's not constant. So let's say this is T0, the pure temperature for the normal boiling. This is T1 and this is T2. Notice there's increase in temperature. And as I'm adding all these things, the vapor pressure is reducing. Once you add solutes, vapor pressure will reduce. It will reduce in the sense that as you add that solute, the vapor pressure that was up will have to drop, because it's vapor pressure that activates boiling. So it will have to drop. It's no longer going to get saturated where it exceeds or it is in excess. It will have to drop. So it drops to P1 and P2. So notice this is for A, and let's say I have this now drop up to this point. then I have this drop up to this point. I notice that this one is because of this. This one happened because of this. So if we want to check now, let's say I call this point. Let's say I call this point from this point to this point and this point to this point. Notice that whatever I have from this point, let's say this is E, or let's say this is Z. Yes, okay. Now let's say this is A. Let's say this is B. Let's say this is C. Let's say this is D. Let's say this is E, F, G. Yes. And let's say this is H. Now notice that everything that happens from A to B should be equal to B to C, because this is the point where we had the difference. Because from this point to this point, from this point to this point, it's time for it to boil, normal boiling. But when I added a solute, change was experienced. So for that reason, from B to A should be equal. That is, B to A gives me the temperature change. And that temperature change came with change in boiling, in vapor pressure. B to C, that is change in vapor pressure. So B to A should be equal to B to C. So B to A should be equal to B to C. Then let's go again. That is B to A equal to B to C. Now let's say we do B to H. B now to H should be equal to, that is time from B to H, that is from T0 to T2, that is change, should be equal to the time when we now have, because that is when we added the second solute, it should be equal to when we now have the change in vapor pressure the second time. That it should be equal to B to E. So B to H is equal to B to E. So what this means is that if you check it, we are trying to see if we can, how to get the difference in the changes, and which means that C to E is equal to E to F. Or you say C to D is equal to E to F. I saying is C to D is equal to E to F, and which means that, see, let's say this is I, or say this is J. That means that D to J is equals to D to J is equals to D to F. D to J is equals to D to F. So let's just write it out. D to J is equals to D to F. D to F. So by the time we analyze this now, we will now be checking it in such a way, you know that it is always increase that subtracts, or you subtract decrease from increase. So let's now be checking. B to A is simply when we increased from temperature of pure solvent to temperature of solution. So it's the same as saying T1 minus T0 is equals to B to C is correct because this is increased. This is the highest. This is the highest. Vapor pressure is highest when you are talking about the solvent. Once you add solute, it drops. So P0 will always start. So B to C is the same as saying P0 minus P1 all over B to H. B to H. So the increase is T2. So it's supposed to be H minus B rather. But we just use B2 and this to be able to get it. Then we now take time and analyze it well. So this should be T2 minus T0 is equals to, so it's already, let's use one equality all over then B to E is proper. So P0 minus P2. So you see, this is actually proper. So even if we choose to use D to J, it's still the same thing. D to J is simply P1 P2 P1 minus P2, because P1 is greater than P2. Remember that this side is decrease. Once you are following the arrow reads increase, because this is plus y-axis, this is plus in x-axis. So anything this way is negative, anything downwards is negative. So then d to j is simply T2 minus T1. So what we are using this graph to get at the end of the day is your ability to get the change in temperature. So you can see that change in temperature is actually equal to change in pressure. That's the whole idea. So change in temperature is equals to change in pressure. So which means that whatever I have for this, whatever value I have for this, remember that change in vapor pressure, we've gotten it before, and is this. Change in vapor pressure is equals to this. This thing means change in vapor pressure and is equals to this. Which means that if change in vapor pressure is equals to change in temperature can also be equals to this. So change in temperature can also be equals to, that is, and this value, remember, this is from here, Kp, that is x2. Change in vapor pressure is equals to mole fraction. Mole fraction, if you remember. So if that be the case, you need to know, you need to take awareness of this. So, and if this mole fraction is happening, it always occur at a point where I will have a boloscopic constant. So this value, this thing that we have here, is supposed to be in such that as we've added this, we should have, it happens, both the vapor pressure, everything about this happens when we have a boloscopic constant, which is at, when, and I said a boloscopic constant is when 1 mole of a solute is added to 1000 grams of solvent. So this particular value should have Ke, a boloscopic constant, and this Ke happens when we have 1000 grams of solvent and we have 1 mole of solute inside it. So this is the complete formula, which means that this can also have the same thing since they are equal. So this is simply Ke times x2 times 1000. Very important. So once I know this, I can now be able to analyze this. A boloscopic constant, I've told you that a boloscopic constant is defined as the elevation of boiling point. Is defined as the elevation of boiling point when 1 mole of solute is added to 1000 grams of solvent. So this can be the same thing as saying, this is the same thing as saying RTO square all over 1000 times latent heat of vaporization. Then this one is the same thing as saying M1 times W2 all over M2 times W1 then times 1000. So this is the formula. This is the formula for elevation of boiling point. So you need to note it. This is the formula for elevation of boiling point. Very important you note it, because as we start solving question, you start to see us make use of this. So I think in order for you not to get confused, I want you to have it in mind that in order for you to not to get confused, I want you to have it in mind that this boloscopic constant it happens when we have boiling point and freezing point. For lowering of vapor pressure, we don't include it. So for relative lowering of vapor pressure, we stop at this, just this, W2M1 all over M2W1. But the minute we are talking about elevation of boiling points, yes, even from the definition, we have no business with it. So remember we said that a boloscopic constant is defined as the elevation of boiling point when 1 mole of solute is added into 1000 grams of solvent. So this is the formula for calculating boiling point elevation. Ke times mole fraction times 1000. So from here we can make M2 subject of the formula. As we start solving question, you see how we do it. So I said that ebullioscopic constant is the elevation of boiling point when 1 mole of solute is added into 1000 gram of solvent. Another name for it is molar constant. Another name for it is molar constant. Why we call it molar constant? That is molarity. Remember that molarity is equals to mole over kg of solvent, and 1 kg is equals to 1000 gram. In chemistry, we use gram, not solvents. We use gram, not kilogram. So a mole is the same thing as saying mass over molar mass. So all over 1000. And this is the same thing as saying W divided by M over 1000. So it's the same thing as saying W times 1000 over M. So 1000, W 1000 times 1000 all over M. So if I carry this molarity now and come, if I carry it and come to times what I have here, which is what is it called? W2M1 all over M2W1. If you see, if you bring these two together, this will cancel this, and this will cancel this. 1, 1. This one should likely be 1. So we now have W2 1000 all over M2. Are you seeing it? So if you check it, you see that this molar constant is what you carry when you are doing Van Hoff's factor. So try looking at it here. We are keeping it that this cancelled this, so we can make use of this. You've seen how we got 1000 up here, but if it's confusing, you just notice that the 1000 comes when we take it that we have that 1000. Whenever we are talking about ebullioscopic constants, there must be presence of 1000 gram of solvent. That is why we have this formula. If using molarity will confuse you, remember how I did it in class, that the minute you finish this, you need to remember that it is molarity of solutes that you've gotten here. Then you need to introduce that of solvents, weight of solvent, and then molar mass of solvent. When you put this together, it's still the same thing that you have here. Still the same thing. So let's move to the next one. We've not started solving question. So this is just to get you to be aware of the 4 colligative properties. So the 4th one is what we call freezing point depression. Freezing point depression. So first of all, we know that freezing point is a state. Freezing point is a state where liquids change to solids. So the phenomenon whereby liquids change to solids is known as freezing, while freezing point is the state at which liquids change to solids. Very important, you know that. So if I now talk about freezing point depression, you can say that freezing point depression is simply the delay or decrease in temperature of solution due to its concentration. Another way to define this is simply the difference. You can also define it as the difference in temperature of pure solvents to the difference in temperature of pure solvents to solution or you say the difference in temperature of pure solvents when a solute is added to it. So I think this is the best way, the difference in temperature of pure solvents to solution, full stop. So if I know this, what it means is that if I have, for example, water, I know that for water to move from liquid to solid, it has to decrease in temperature up to 0 degrees C. Now let's say I come and have water, then I come and add something like glucose inside it or anything at all. It's not really even, that's why in some cases you see they add things like salt to road to prevent melting. Sometimes even in car what's it called, car engines, to prevent it from like blocking. So you see, what I'm trying to say here is that for the fact that you've added something to that solvent, if the normal temperature it takes for it to freeze is 0 degrees C, it will cause it to take more time. It will cause it to take more time in order to freeze both the solvent and the solution. And since freezing has to do with decrease in temperature naturally, it simply means that that's delay in it getting to the freezing point causes it to delay more, to decrease more. So that decrease or the delay in the temperature as you try to freeze both the solvent and solute, which is solution, because solvent plus solute gives you solution, that delay in the temperature is what we call freezing point depression. So now that you know this, let's try to get a graph. So if I add this now, you see that it will now give me maybe lesser temperature. It will give me maybe -5 degrees C, which you know is less than 0 degrees C. So let's try to draw a graph for this. If I have this to be, it's always vapor pressure against temperature, but this time is temperature of freezing. So let's say this is temperature. Why I'm drawing this is so that if in your exam they ask you to draw vapor pressure against temperature, you don't get confused for freezing points. So let's say we know that vapor pressure of solvents is always the highest. Once you add solutes, you need to know this. In fact, see how I normally teach my students. You need to know that for relative lowering of vapor pressure, and then freezing points depression, you need to know that these two, once solute is added, it will go down, it will drop. Then you need to know these two. While for boiling point elevation of boiling points, and osmotic pressure, you need to know that these two, once solute is added, it goes up. Yes, reason is because naturally it requires temperature going up to achieve. So if you happen to put anything solute, it will take more time for it to increase that temperature. Why these two? It requires temperature dropping for it to occur. So if you add anything more solute, it will tend to bring it down. So if I have this now and I add solute A, That's, let's say this is solvent, sorry. Let's say solvent is represented with A here. Then let's say I have solute B, solute. So let's say this is a solution. Once you add solute to solvent, it becomes a solution. Then let's say this is C, solution 2. This one is solution 1. Now notice that if I happen to, let's say I happen to let me call this A, sorry, solvent. This is my solvent. This is my solution. Yes. If I happen to heat this, sorry, try to freeze this at 0 degrees C, the temperature will drop and it will turn to ice. Now, if I happen to add a solute B, solution, and I try to freeze this solution, it will require it to take longer temperature in order to decrease. It will take longer time for it to freeze. That taking of longer time, since temperature has to go down for freezing to occur, taking of more time due to the addition of solute is what we call freezing point depression. So it will take longer time. So this might be around maybe minus 5 degrees C. But let me just use TB. Let me use TB. That is temperature for the second solute. Then this one will drop again. Let me use TC now. Temperature for the second solute. That is second solution. Then this one now is TA. That is, and is at 0 degrees C. That is temperature for pure solvents. So notice that it dropped. And see, this P0, or you say PA, is for this one. This is when it occurred. Why this one is going to happen somewhere here, that is PB, vapor pressure of the second of the solute. Then this one should be vapor pressure of the second solute. That is second solution, or that is solution. The first solution, the second solution. This one is solvent. Let me not confuse it. I believe you understand it. So now see, if I finish this and I want to get the difference in the change, let's say I call here now, this is A, point A, this is point B when this occurred, then this is point C when this one occurred. You will very well notice that if I have this to extend, let's just, so that we can be able to illustrate this. If I have this way, you can see that whatever happened from this point to this point, this is where the change on temperature started. From A to B, this is this to this, the decrease gave rise to B to what I have here. Let's say this is Z, gave rise to B to Z. So we can say that A to B is equals to B to Z. That is, it dropped in temperature. Temperature of solvents dropped from this point to this point. And as it dropped, its vapor pressure dropped from this point to this point. So it's equals to B to Z. Now let's check for the second one. This second one. You can see that from A to C, is equals to C to, let's say this is Y. Let's say this is Y. So from A to C, from the point where it dropped from in temperature from A to C, that is where the vapor pressure also dropped from C to Y. So as it dropped in temperature from A to C, it also dropped in vapor pressure from C to Y. So we can say that A to C, is equals to C to Y. I see it, which means that from this point to this point is decrease in temperature. Decrease in temperature. And also from this end to this end is also decrease in T, in temperature. While from this end to this end and then from this end to this end is decrease in vapor pressure. So we can very well see that A to B is the same thing as saying T naught or TA naught minus TB all over TA naught minus TC. That is A to C now, A to C, TA naught minus TC, then equals to B to Z, B to Z, B to Z is the same thing as saying PA naught minus P. That is vapor pressure of solvent minus vapor pressure of the first solution all over of solution B. Then C to Y is C to Y. That is vapor pressure of pure solvent minus vapor pressure of second solution, or you say vapor pressure of solution C, which is P naught minus PC. So if you look at this, where you can see that change in temperature, and this time around is decrease in temperature. Whenever there is decrease in temperature is freezing point, while whenever there is increase in temperature is boiling point. So change in temperature, decrease in temperature is equals to change in vapor pressure, which is also decrease. So since they are equal, you can very well see that the same formula can apply to freezing point. So to calculate freezing point, we can say since we know that change in boiling point is always equals to W2M1 M2W1. You can write it for this as well. Since they are equal, that means this one can also be W2M1 all over M2W1. But know that it's only relative vapor pressure, lowering of vapor pressure, that occur at this. When it's freezing point or elevation of boiling point, it can only happen when we have cryoscopic constant. And this cryoscopic constant is simply the freezing point depression when 1 mole of solute is added to 1000 gram solvent. So I need to always introduce this. So this is going to be times 1000, and this 1000 happens when I have the Kf, the constant Kf. So it's very important to know this, and this Kf will always be given. The same thing with Ke. You need to know that ebullioscopic constant is presented with Ke. The same thing with this Ke. This is ebullioscopic constant. It's always given. If it's not given, you use this formula, the formula I gave you for it, which I told you that ebullioscopic constant has a formula which is RT, and this T naught is, this R is the gas constant, this one is T, temperature of pure solvent raised to power 2 all over 1000 times latent heat of vaporization. So if it's not given, you use this to calculate it. That will give you. So then that means that I need to know this formula. So we can also say that TF, change in freezing point, is the same thing as saying mole fraction of solute, because you notice that everything here is gotten from mole fraction of solute. Then times Kf, which is freezing point cryoscopic constant for freezing point, then times 1000. Very important you note this formula. Very important. So now that I know this, we've now started calculation. Let's look at osmotic pressure. Then we are done for today, so that in our next class we'll now start calculations under colligative properties. So for osmotic pressure, For osmotic pressure, first of all, you need to know that osmosis, when we talk about osmosis, you need to know that it is the opposite of diffusion. We know that diffusion, another name for diffusion is dilution. When something has to move from high concentration to low concentration, you say it's diluted, you are diluting it. But when something has to move from low concentration to high or higher concentration to a higher concentration, we say that is osmosis. And the difference is that this osmosis occurs through a semi permeable membrane. By permeable, semi-permeable membrane, we mean it is something that does not really allow flow. It is very gradual. Example, in living things, just like when you are boiling potato, you put water, you put potato, put yam. The fact that it boils is gradual. Water has to be entering inside it gradually filling up the spaces, because inside that potato or your yam, it has more walls. It has a higher concentration to accommodate that water. And when it gets to a point, it starts boiling. You say that it's done. That is exactly the idea of osmosis. The same thing applicable in human beings. Like when you put water, you bath or you do anything or you are sweating, it takes time for those sweats to pass through your skin. So that is just the idea. I'm trying to make you get the idea. So in osmosis, we are thinking of low concentration to higher concentration through semi-permeable membrane. And if I have this idea, when I'm not talking about this in terms of solvent, it is simply the movements of pure solvent towards the solution parts, or you say towards a solution. So for example, if I have say a bowel and I have water here, I have solvent here, and here I have solvent plus solute, and what is separating it, let's say this is the semi-permeable membrane. Let's say this thing you have here is the semi-permeable membrane. So you will notice that water, semi-permeable membrane, water will move from the parts where you have water to a higher concentration, because it will tend to be drawn towards the parts with solute. It will be pulling it more. So through this semi-permeable membrane. Now, on addition of solutes, like more solutes that you add, more and more solutes that you add. So remember I said osmosis is defined here in terms of movement of pure solvent towards a solution, towards the solution part. So on addition of solute, as you increase the solute, it will tend to make water come towards this end more. Now, as you increase this solute to a point where it becomes too much and you apply pressure, let's say you apply pressure here, hydrostatics, you apply pressure on top of this. If you apply this pressure, what it will do is that it will squeeze the solute. And remember that the solute we are dealing with here is things like maybe glucose, sucrose. Remember the idea I gave you when we started, urea, kerosene, for example, all those octane and the rest. So when you squeeze it, you see that the pure solvent will have to pass through this permeable membrane to come back to the part with water. And if you do this for long, a point will come where all the water inside this side will move towards this end. So that pressure that you applied is what we call osmotic pressure. So we define osmotic pressure as the pressure applied to solution, in order to prevent osmosis. Or we can say it is the pressure applied to solution in order to make the pure solvent, move towards the parts of pure solvent. And notice that sometimes if you have water and you, for example, carry stone and put inside, put things inside, the water will start leaving while the solute will be going inside to settle down. So as you increase the solute as well, to a point it will start reversing even without applying pressure, but it is just going to be little. As you increase the solute, at a point it will start doing the opposite of what it could have done when it is normal. So as you increase the solute, at a point it will start pulling the water away. When it absorbs, it will start pulling it away from it. So that is why we say that more concentration causes osmotic pressure to increase. So you need to remember this part where I listed this. So elevation in boiling point increase, osmotic pressure increase. You need to know this. So, but this our work cannot be complete if we fail to talk about Van't Hoff. A man called Van't Hoff is the one that gave us the equations of osmotic pressure, and he did this using Boyle's law and Charles' law. So the first law he called it Boyle's Van't Hoff law. And what he said here is that the pressure applied to the solution is directly proportional to the concentration. Or you say pressure is directly proportional to the concentration. What do I mean? I normally tell my students to assume pressure to mean collision. Even when you have vapor pressure, at a point once it starts colliding, the molecules start colliding, you see boiling. If you have a classroom, you add more people. The more people you add, it causes stress. You see that there will be collision. But if you reduce the number of people, that is why we say that if you have more concentration, there will be more pressure. If you have more particles, more solutes, there will be more pressure. And that is why even concentration, if you remember, concentration is regarded as molarity also, is equals to mole over volume. Notice that this is the sentence that says mole times 1 over V. So you see that even concentration varies inversely with volume, which means that if I have pressure varies inversely with volume as well, which means that if I have a container and I have maybe 50 cups of rice inside that bucket, inside the pot, if I increase the pot, you see that the cups of rice or whatever particle I have there will have more space. So as you increase the space, the volume, the concentration tends to be smaller. While as you reduce the space, the concentration tends to be bigger. So if you have this knowledge, if you have this idea in terms of collision for pressure, you need to know that these two formulas are the same thing. So pressure is directly proportional to concentration, and we use M for molarity for concentration, and pressure is inversely proportional to volume. So they are the same thing. So his law states that pressure is directly proportional to concentration and inversely proportional to volume. So from there we move to the second law, which is Charles Van't Hoff law. And this Charles Van't Hoff law is gotten from Charles' law, which states that at constant, remember that this one, Boyle's law, is at constant temperature. So Charles Van't Hoff law states that at constant pressure, that volume is directly proportional to temperature. What do I mean? If you blow in air inside balloon, the more air you add, you see that balloon will start to expand. The volume starts to increase. At a point, it will burst. Just like maybe you put water on fire. If you start hitting that water, what will happen is that it will try to be taking over the walls of the container to occupy more space. The particles will gain kinetic energy. The one up come down, the one down go up. But at a point when it starts doing this, it will get to a point where it now fill up the whole space. We say that vapor pressure has occurred. When it gets saturated, it starts boiling. And if you keep eating this water, it will take over the whole space, start boiling vaporize and leave the whole containing vessel. So we say that more heat, temperature, remember what temperature is, degree of hotness, coldness of a place, particular time. So if I know this, which means that any increase in temperature causes volume to increase. And if it is too much, if it gets too saturated, it will cause everything there to vaporize or to break. So if I have that idea, it simply means that if I apply temperature here, as I apply more temperature, be it in form of heat or in form of enough force, as I apply more air to this, that whatever temperature, means of temperature I apply to this will cause this volume to expand. And in trying to expand, as it is trying to expand, it will have to release. The pure solvents. So from these two laws, he was able to use the idea of ideal gas. Ideal gas equation. And you know that ideal gas equation is simply the combination of all the laws of gases, which is PV equals to nRT. So if you know this, he was able to use this and these two things, this Boyle's law and Charles' law, to create a law for osmotic pressure. And remember, osmotic pressure is represented with pi. So he simply said Boyle's law gave him molarity. That is, osmotic pressure is directly proportional to molarity and also directly proportional to temperature. Then he introduced the gas constant. Which is R. So we say that pi is equals to mRT. Osmotic pressure is equals to molarity times gas constant times temperature. And remember that molarity is the same thing as saying N over V. So N over V RT is equals to pi. So in most textbooks, you will see this as saying pi V is equals to nRT, if you know what I mean. So anytime you're asked to calculate molecular mass of a solute, is always of a solute. Remember, the idea of colligative properties about what is happening to solvent because solute was added. So any molecular mass I'm calculating will always be of solutes. If stated otherwise, maybe they are just trying to push you, because the solvent is always known. And if I know it's water, I already know the molecular mass. So, and from mole, we have that mole is equals to mass over molar mass. But remember, I told you that here we are using weight for mass and using m for molecular mass. So I'll replace mole with W over m, then RT, pi V equals to. So if I know this, making subject of the formula, I will have m pi V is equals to WRT. Making molecular mass subject of the formula, I have pi m is equals to WRT all over pi V. Very important. So this is the formula I use to solve for molecular mass whenever I'm asked to find molecular mass of a particular solute that experienced osmotic pressure, or if I'm asked to find osmotic pressure and I'm giving concentration, giving temperature, I can simply put by gas constant whatever they've given me to find my osmotic pressure. But in a situation where I'm giving volume and giving mole, giving gas constant and giving temperature to find osmotic pressure, I just use this formula. So it's important you take notes of everything we've done here, much as I'm trying to be fast so that I can make good use of the time and save time as well. But if you take time to watch this video over and over, calm down to make notes from it, I believe I've been able to cover every useful thing you need to know when it has to do with colligative property, which is your chapter 4 that talks about system. All right, please, thank you very much, and do subscribe to the channel. Good number of you, I notice you watch these videos, and when it gets to the end, you say thank you in your mind and you leave. It's not good for the channel. So do subscribe to the channel and remain blessed.